Hey everyone, welcome to the Machine Learning Mini Symposium. So we'll start off with pretty much an hour of Reactant. So Billy will start with Reactant. I will do a Lux demo for Reactant. So William is an assistant professor at UIUC. He received his PhD at MIT in computer science. He is well known in the Julia community for his Enzyme.jl project, which basically autodiffs through LLVM code. And he also, apart from that, has worked on a lot of C++ side, polygeist, Tapper, right?
The taper, yeah.
Yeah, so a lot of this cool stuff, which he's also going to talk about today in his new project called Reactant. So
Yeah. Thanks, everybody. This is actually my very first JuliaCon, so I'm very excited to be here. So to start with, like Avik said, I'm going to be telling you about a cool project that we started recently called Reactant. And there are so many people who have worked on various pieces of it that I couldn't find the pictures of everybody's faces offhand, so I at least have all of their wonderful names up here on the board. To sort of start this off, something that I, as a computer scientist, and in particular I as a compiler person, really would like to get fixed is that, usually when you go ahead and write code, the code that you write often has a significant mismatch between, how you want to write it and how you want to go ahead and execute it. So here I have a fairly simple Julia, algebra expression where we have, some matrix X, we square it, we add it with the transpose of X squared. So let's go ahead and see what happens when we actually want to go ahead and run it. It turns out that under the hood, Julia does a lot of things. So the first thing is we have that first X squared, and Julia will allocate a new array for the result of X squared. And of course, inside of that, it'll do a mapmul. Then, of course, we have our second X squared over there, and it'll once again allocate now a second array, and once again, do another mapmul. Fortunately, Julia is very nice, and the transpose for us doesn't allocate now a third array, just does it inside of types, which is fantastic. But we're not done with our allocations yet. We have one more allocation. When we add up these two arrays together, we're going to allocate yet another array, and then we're going to actually do the add inside of it. We can summarize this as following. We have 3 different array allocations, 2 mapmuls, and 1 add. So that's cool. That's probably how I'd want to write it. It's how it appears maybe in like some physics equation or whatever else. But that's a lot of allocations, possibly mapmuls, and that extra add there. Anyone have any ideas how we could possibly speed this up? Because I'd like to speed this up at least.
Add a dot because you think a plus equals dot, so that you get to the addition in place. You're probably going to throw away, so say 1 allocation.
Yeah, do an addition in place plus equals would save 1 allocation. Anything else that I can do?
Reuse the wishbone.
Yeah, reuse that same X squared so we don't do it twice. Any other sort of funky things? Not a fan? Well, fortunately, there's a whole sort of diversity of things that we can do. So let's talk about that, try to reuse the initial allocation. So one thing that we might be able to go ahead and do is, transpose X squared, if we assume it has, the nice properties that we want to assume, is just the same as, calling X squared again. So let's just go ahead and say 2 times X squared here. We're saving it. We dive into it a little bit more, and now there's 2 allocations. So we have the X squared allocation, but we still have 1 allocation for that multiply by 2 to put it inside of there. We've reduced the number of mapmuls though, so mapmuls are expensive. We really want to get rid of that. We no longer have that add, but we now have this mul here. So that's, 1 allocation at least a little bit better. Any other ideas for things that we can do? So I don't fault anyone for not knowing this, but if you look inside the linear algebra library inside of Julia, or in particular, if you spent too much time like me at one point staring at the insides of blobs, it turns out that the multiply utility itself is, slightly more general than just like A times B. It turns out the actual runtime call is saying that, the output matrix C equals the old output matrix C times some number plus the mapmul times another number. So in fact, inside of that mapmul, whereas it's normally by default set to, multiply X times the number 1, and then plus 0 of the old output here, we could do this without that extra allocation, without that extra 2 even, all inside of 1 mapmul utility by just cleverly shoving that extra square inside of there. So now we have a much nicer version, 1 allocation, 1 mapmul, no extra stuff inside of it. Beautiful. No one wants to write that. I mean, like, some vague amounts of performance engineers can write that, and sometimes you have to write that. But my overall question here is, can we build something that enables us to not have to write this? especially because as soon as I want to go to, say, a different device, or worse, multiple devices, the types of optimizations, and this is still like a fairly general purpose version, we haven't done any fancy tiling, vectorization, whatever else under the hood here to truly maximize performance, is going to differ a lot from device to device, let alone from the math at the very top that we wanted to start with. So before we talk about how we can go ahead and fix this, let's talk about why the current systems don't fix this for us. So there's a wonderful utility inside of Julia called code type that will show you the sort of insides of how this gets compiled. And it turns out that the code type of our original code basically says, hey, you have your multiplication, Hey, we're going to go ahead and allocate now this sort of temporary variable here. We're going to go ahead and do our wonderful adds inside of this temporary variable, and then we're going to go and send it off. And one thing that you'll immediately notice here is these generic sort of pseudo runtime calls are very non-obvious what they're doing. To us, we know what they're doing because we knew it came from our high-level linear algebra, but to the Julia compiler, this is just some generic function call that could mean anything. It could touch all memory. Who knows what's happening under the hood? And it actually gets a little bit worse than that if you just look inside of one of those map moles. This is a shortened version, because I want to at least pretend like it fit inside of a slide, of one of those multiplies. You see at the top we have all of these extra allocations, we have these type pieces, we have these comparisons. Eventually we have this generic map mole, which like 3 steps down the compiler will eventually hit our wonderful gem utility, where we could have added that extra 2, like we talked about earlier. Suffice it to say, getting down to this level, or even from the top level down to that one place we could add that to, is really hard. So now I'm going to talk about this wonderful utility, or specifically compiler engine called MLIR. You've probably heard of LLVM. It's the default used inside Julia, as well as like Swift and basically every other language itself. MLIR, still part of the LLVM general ecosystem, but has a few key nice things. Specifically, unlike LLVM, where there's a predefined instruction set, which basically mirrors a C-like or sort of pseudo instruction level semantic, the definition of all of the MLIR instructions is completely up to the user. So, I or you or anyone else can define a new instruction that has whatever custom semantics that I want it to be. There's tons of these that already exist, some of which I actually helped develop, including those that say we have a built-in instruction just for linear algebra, just for GPU programming, for fully homomorphic encryption, and your imagination here can really go run it wild. It turns out the other really nice thing about MLIR is it lets you mix and match all of these different pieces together. So you could define a new dialect and combine it with my dialect, and we could do optimizations across these boundaries very effectively. It's so useful, especially the sort of linear algebra and the sort of accelerated programming sort of backends to MLIR, that nowadays all of the core infrastructure for machine learning, basically at every company, all goes through MLIR, be it JAX, PyTorch, TensorFlow, Triton, name your favorite sort of thing, it goes through MLIR to do codegen. And it turns out that there's plenty of really cool front ends that exist for MLIR, e.g. in C++, we've built a tool called Polygeist, and in this talk specifically, we're going to be talking about Reactant. And a cool thing, just to give you like a little bit of a demonstration, I don't know if you've ever seen LLVM IR before, but it's very similar to that Julia IR, if not slightly even more verbose for those who have gotten some errors in the past. The MLIR version looks something like this. It actually appears to have a for loop. It has a store with some indexing off it. Looks fairly pretty. And the fact that it looks fairly pretty means that the compiler has that extra information to do nice things about it. So to give you some further intuition about why MLIR itself is useful, let's talk about GPU programming, and I'm going to be a bad person here and talk about GPU programming in CUDA and C++ before we get to inside of Julia. So one particular problem that GPU programming has is that those existing compilers, be it LLVM IR or even the Julia compiler, though recent work like Taper tries to fix this, doesn't have a good representation of parallels. So here we have sort of a vector normalization. So we call this normalized function inside of the normalized kernel itself. We call this extra sum here. But it turns out, if we're summing over that input and we're only storing into that output, the value of that sum is not going to change per kernel iteration. So we're doing a ton of extra work every single kernel. In fact, we're doing O of n work for the entire kernel to be able to do that. Something that I'd really love to do is to be able to move that sum, hypothetically speaking, outside of the kernel to be done once, saving all the work across everybody. But even if it were possible to do that as an optimization, which even LLVM for regular CPU code cannot do, the GPU makes this incredibly hard. Specifically, you have 2 modules, one for the host code, e.g. all the calling context around it, and one for the device code. And these 2 pieces can't see each other. which means that in practice, not only can you not sort of move some code here all the way over to this area, it also means that, you don't even know how many threads you're being called with, or if these things don't alias, or any other sort of, passes that would enable some nice host device crossing optimizations. We built this wonderful compiler called Polygeist. It works in C++, but it also, does a ton of optimizations for generic GPU and synchronizations. And effectively, if we compile this into MLIR, Polygeist style, we have a nice parallel for loop representing the GPU as follows. This enables us to do exactly that optimization like I talked about earlier. We could hypothetically move it outside of the loop. We could reschedule our kernels, figure out what the optimal shared memory size, block size, all those other sort of wonderful things, do kernel fusion, host device optimization, tons of really nice things, including taking our GPU code and transforming it to go ahead and run on the CPU. And one thing that I'll say that we'll come back to in a second here is all these optimizations that we're doing on our original code from many Enzyme papers that we've done in the past demonstrate the fact that if you do more optimizations on your code before running autodiff, you have a much, much faster derivative code as a consequence. Another sort of set of reasons why MLIR could be useful for us here in Julia. So we went ahead a little while back and we wrote a bunch of linear algebra optimizations for effectively a linear algebra dialect inside of MLIR. So here we have like a generalized dot product, right? A map mul, we have an element-wise multiply and an element-wise add. We wrote 200 plus of these, linear algebra simplifications. Some of these are easy, like, x plus 0 just goes to x. Some of these, are a little bit more tricky, like, transpose of x is itself, or transpose of map mul is swapping the input orders, and tons more complex things as well. To give you an intuition, again, for why this is useful, here we have our little simple code that has, 100,000 sized input tensor that we do some dot products and other stuff too. But it turns out at the end of the day, we only want the first 10 elements, which means we're doing all of this extra work here because, we're only going to see those first 10 elements. So if we're going to just go ahead and add up 100,000 things and only slice off the first 10, it's way better if we could just slice off the first 10. So we do that. We push the slice up. And, now that our B here, which multiplies, 10,000 or 100,000 things together, is only using the first 10, once again, we can supply the same optimization and only do the first 10 elements from those pieces, and so on and so forth, and really propagate across your entire program the sort of linear algebra, mathematical, and other properties. And, we built this inside of MLIR, which, like I mentioned, is used inside of all the big ML frameworks. And just for fun, we applied this inside of JAX in a state-of-the-art neural network training, like the Gemma equivalent. This isn't the sort of version of Gemma/Gemini that's run in production, but a version of this sort of standard machine learning model that Google runs for all of the big things. And on a 32 TPU accelerator case, we got a 53% speed up in training by applying all of these linear algebra optimizations over standard JAX because of the need for both that linear algebra and then the combination of that with the automatic differentiation. For a single accelerator, we still get a fairly reasonable 14 to 18.5% speed up, which, considering that it's many people's jobs at Google to keep these, machine learning models running as fast as possible on, the hardware that they themselves build, being able to apply a couple of transpose rules is a fairly significant win. And if you're more curious about some of the logistics here and how we did this, there's a paper that we published at last CTO also introducing the transform dialect. So that's all very fun. But let's get back to Julia. This is JuliaCon after all, right? So with that as a premise is why MLIR and a lot of these other cool things like, user-defined optimizations are particularly cool, we built Reactant. Effectively what this is, it is an optimizing compiler framework for Julia built on top of MLIR. So we can directly preserve all of that high-level mathematical and other semantics directly into the compiler. And this gives us a lot of really interesting benefits that I'll talk about. We can now optimize programs just like we saw earlier, doing all those fancy linear algebra pieces. We can also effectively retarget programs. You can write the program once with whatever sort of form of linear algebra that you want for your one node system. And we will automatically figure out how to retarget it, one, to your favorite accelerator, be it CPU, GPU, TPU, graph core, whatever else that you like, including distributed clusters of that, inserting all the communication commands for it. We leverage something called XLA, which is the state-of-the-art sort of parallel runtime used inside of all of these big ML frameworks, giving us, when combined with our optimizations, substantial, speed ups. And, we're workable with fairly general purpose Julia code. We support mutation, we support control flow. I'll talk more about that in a second. Autodiff, all the likes, and this is all open source, of course. So to talk a little bit about what Reactant is, or specifically how to use it, there are 3 important things that you need to know. So first, we have this concept of a reactant concrete array. We have a compile command, and we have a reactant traced array. I'll talk about more of these in detail in a second. A simple way that you would go ahead and use Reactant is shown here on the left. Of course, we go ahead and we import our wonderful package. We have this conversion, Reactant to our array, which will take a generic Julia data structure and then sort of convert all of the inner arrays to be Reactant-owned memory. The reason why this is important is obviously if we're going to go ahead and run this on a machine or distributed set of machines, this lets us define an array that could be accessible on any piece of memory, including, again, sharded across multiple devices. We have our standard Julia function that we want to go ahead and use, and we have this wonderful compile command. What this compile command does is, given the function you want to execute, and then the various inputs, it will perform partial evaluation of all the non-reactant sort of inputs, effectively getting rid of type instabilities, getting rid of garbage collection. We'll see a little bit more about what that is in a second, and have a wonderful compiled version of our code here that now we can execute incredibly quickly for any arbitrary input. And of course, we go ahead and actually execute it. So talking a little bit more about that conversion, like I mentioned a second ago, we have some nice helper utilities here, Reactant to our array, that'll take an arbitrary Julia struct and recursively go through and convert all the pieces. We see, in fact, even when we initially load Reactant and do it, the machine that I was running on happened to have a GPU, so as a consequence, we're using GPU memory for this. No extra modifications required. We see here that the result of our execution here is a concrete or reactant array, and of course, like I mentioned, Reactant found that there were 2 5090s, so it decided that's what it was going to use, both for the execution as well as the storage. And you can change this. It figures out by default what the best things are on your system. Second piece is compilation. Now, this is a little bit long. I'm not going to run you guys through this, but this is what Reactant initially sees by tracing through and compiling the Julia code. So effectively, all of the underlying pieces, there was a broadcast somewhere inside of it, there was a conversion, there was all these wonderful things. But one thing that you don't see here is you see no garbage collection calls, you see no type instabilities, you in fact see the type for literally every one of these pieces, which is relatively nice. The other thing I'll say is this is obviously before optimization, because we have a nice little flag there at code HLO optimize equals false. So we can optimize it. We can run through those 200 plus linear algebra optimizations and the like, and we get this code here at the very, very top, which is a .general aka matmul, transpose, and add. And in fact, we did the common sub-expression elimination for us, so we didn't do any of the extra pieces. The second piece here sort of represents the sort of direct runtime that we're actually going to go ahead and do. And if we look very closely at it, right here, specifically. This is just a single call to Kubla's dgem, meaning that we successfully turned this original code with all those sort of fancy things into a single matmul call with no extra pieces inside of it, which is, again, pretty fantastic. The last piece that I'm going to talk about are these sort of traced arrays, like I mentioned. So Reactant has 2 types of arrays, like we talked about a second ago. Those concrete arrays, which is where you go ahead and store your data. It can represent data stored across multiple machines or whatever else that you want to do. It's where you have all the pieces, similar to your CUDA array or whatever else. A traced array is slightly different. This is the array type inside of the compile command itself. The reason why is this represents data that is not a compile time constant, and effectively represents values that we're sort of generating all the code for, but we don't necessarily have those values at this moment for you to be able to use. So if I had this show here to the original command, we now see that our x inside of here, whereas x outside of the compile was a concrete array, our x inside of here is now a traced array. We can see both the pros and the cons of this approach. Like I talked about earlier, the pro of this approach means that, we've gotten rid of all of our type instabilities, we've partially evaluated all these wonderful things inside of it, but like I mentioned, you don't have the values of those pieces of data inside the code when you're compiling it. So here I go ahead and make a reactant traced number. The default is to trace all the arrays and not the numbers. If you want to trace the numbers, we have an extra flag like this. And we have a condition based upon this compile unknown value. And we try to go ahead, and by the way, we have a nice little syntax here at JIT, which just runs compile and then execute compile. You usually don't want to do this because compilation will take a while, but for just doing a simple little test like this, wonderful macro. And we get an error that there's a non-Boolean, specifically this traced Boolean, used in a Boolean context. And that's effectively because at the time of picking which one of those 2 branches to go down, we don't actually have the value. So we need to figure that out. Now, Reactant is actually a lot more general than JAX and these other sort of tracing-based tools, specifically because we actually get all the Julia IR. So we can see all of the original control flow, and we can convert that and preserve that into control flow in the MLIR. Right now, this is not done automatically, though we have some students working with us automatically doing this upgrade for us. But effectively, if you want that control flow to actually preserve both branches of it, we have a cute little macro here at trace that you can apply to an if statement, a while, a for loop, a function call, whatever else. It'll compile a version where you have both of those branches available. And of course, we can go ahead and now run it. Like I mentioned a little bit earlier, Reactant is wonderful in the sense that it lets you write your regular Julia-style code, and it'll automatically distribute it across, whatever your favorite type of accelerator it is. Under the hood, this works by effectively Reactant recognizing all the devices that you have available, or more specifically, what nodes inside of a cluster you might have, though of course it works equally well on my laptop as it does on a fancy cluster of these pieces. And then when it takes that tensor, e.g. the mapmul like we saw earlier, and it sees that there's only 2 devices, it says, okay, I'm going to do a partial mapmul on each one of these devices, and I'm going to send data across that boundary to be able to effectively compute the entire mapmul at once. And this is nice because now the user doesn't need to care about what type of system that they're running on, let alone how many things that they want to run on. We, the compiler, will now go ahead and do our best to automatically figure out how to place these pieces. Notably, a compiler is not magic. We do a good job. We run all these fancy optimizations that can be very, very difficult for a person to do in practice, like we saw a second ago. But this doesn't mean that someone couldn't sort of like expert hand tune something a bit better. But that means we can write a new optimization that takes that into account, of course. And again, the big takeaway here is, you can take your existing single node code, and you don't need to modify it to go retarget all of your favorite different systems. And fun example, we now have JuliaCon Global with TPUs, default with Reactant installed inside of it. You can go ahead and even, run it on, your favorite, 8x TPUs or whatever else. In that case, eight particular devices. To give a brief sort of highlight of how important these types of optimizations are in practice. So, we took the Lux framework here, and we compared running it with the default backend with CUDA.jl, right? Which unfortunately has to make all those, additional allocations and cannot fuse together. You have this mapmul with a bias add after it into one kernel and the likes. And we compare that with Reactant, where we can compile all these things together. We can get rid of those unnecessary allocations. We can fuse kernels together. We can use the super optimized cuDNN by recognizing that this is there. And overall, for various sort of model sizes here, we get between a 5 and a 15x speed up across both the forward time and the backwards, e.g. training time. And if you like this graph, hear more about it in the next session that Avic's going to talk about. A couple of other sort of really interesting things. So scientific codes, as an example, is the state-of-the-art code, oceananigans.jl, has hundreds of handwritten kernels. So whereas, in the first part of the talk, I spoke a lot more on like, hey, we have these existing linear algebra pieces, a lot of existing Julia code equally applies, is written with, custom kernels and the likes, which obviously those existing ML frameworks don't like, not to say that we're an ML framework or a general purpose compiler, of course. But really interestingly, if you look at the ways that the actual ML hardware, e.g. a TPU, was built, it was originally built when convolutional neural networks were a thing. So actually, TPUs are just giant convolution machines. And we happen to put a bunch of things that look kind of convolution or mapmul-like onto it. But if you squint at the type of stencil kernel, which is standard, in this case, inside of Oceananigans and even more general purpose code, it actually looks remarkably similar to a convolution. And yet we don't have any of these existing scientific pieces of code being able to run and leverage the big ML hardware. So another goal of Reactant is saying, can we automatically take the high-level math and other structure that exists in the scientific world and now apply all of the sort of machine learning, both computing manpower and software engineering manpower to it? I won't go terribly deep into all of the details here, but effectively, we have a system based off of Polygeist earlier, integrated into Reactant, that takes your existing CUDA code, we identify effectively the underlying tensor operations inside of it. So first, we find that we have our original Julia code. It becomes the LLVMIR code here. We convert it into those nice sort of affine parallel loops from what that generic CUDA kernel represented. It turns out that we can take our general purpose affine loops and turn them into sort of tensor operations. And finally, we can optimize it into a a gigantic convolution, which is, again, exactly what we want to go ahead and run. And we actually took the state-of-the-art Oceananigans code, which has like 277 plus CUDA kernels, and we compiled the single node version of that CUDA code to run on thousands of distributed accelerators, including, I think it's 2,000 of the now second latest, because there's a new TPU that came out in between, TPUs from Google, as well as several thousand on regular NVIDIA GPUs. One more sort of cute in-progress work that I'll say. I mentioned earlier, of course, that Reactant is compatible with Enzyme, though, again, completely separate project. You can use Reactant without any fancy auditive stuff. But it turns out that running all those optimizations before differentiation is incredibly crucial. That's what makes Enzyme fast in Julia via LLVM right now. All those extra linear algebra optimizations are also extra optimizations we want to run and combine with. So we took this con network, which I can't really tell you what it is, but it's a fancy neural network. We ran it the forward pass in regular Julia with and without Reactant, and we have the backwards pass in this case with Zygote with and without Reactant, and Enzyme on the inside, in this case specifically Enzyme MLIR. So I won't force you to do means because means are hard, but overall here, the original code, compiling it with Reactant, you get a 2.14x speed up. On the backwards pass, that speed up on the primal results in a 13.5x speed up on the actual derivative itself. And again, pretty pictures are fun. So the actual version of the big code that we saw earlier results in some wonderful things like that. So again, overall, Reactant is an optimizing compiler framework for Julia, built on top of MLIR. It lets you preserve all of those original high-level semantics, including discovering that from existing CUDA kernels and the likes. This lets you optimize programs to run faster, and also retarget your programs to run on whatever sets of machines that you like. We work on top of XLA. Again, that's state-of-the-art runtime that's used by all the big ML frameworks, so we are competitive, if not usually faster, than a lot of those big ML frameworks because we have our nice optimizations built in by default. And like I mentioned earlier, we're compatible with most Julia code. We have mutation, we have control flow, we have autodiff, and again, this is all open source. Thank you so much.
Thanks. Hey, excellent talk. Thank you. It looks like we're bypassing CUDA.jl with your package. Is that correct?
No, we are actually using CUDA.jl. So specifically, CUDA.jl is what's used to generate the LLVM code from the original kernels. We're then taking that LLVM code, and then we're converting it into the higher level form. So we're not using CUDA.jl for execution. We're using it for code generation.
Okay, that's really interesting. Thank you. Could you talk about how, if there's any kind of control flow or anything like that that would not be, any Julia code that would not be compatible with the Reactant?
Yeah, so like I mentioned, we want to compile this into a effectively super type stable version of the pieces. So the caveat is either you have to pick control flow where you pick one of the two branches at the moment. So if I go back to this slide right here, right at the top, where if that was a compile time constant in the sense that it was not a Reactant bool, but just a regular bool, it would pick one of those two pieces. That's totally fine. Or the second approach, like I have down here, where this could be a non-compile time constant, it'll emit both of these branches. This second case right here requires that the outputs be of the same type, basically because we need to preserve type stability across our compiled code. So there are some caveats here, but effectively you can have completely type unstable code out the wazoo at the top, but your control flow is limited in terms of the sort of conditional branches that you can make. Or you can have fully general conditional branches if your result types are the same.
Great talk. You mentioned you turn off the GC. Can you go more into that?
Yeah, so it's not necessarily that we turn off the GC, but within the Reactant compiled code here, we effectively make a single executable that runs through all of the internal multiplies, adds, whatever else out there was kernel calls, etc. Which means inside of here, there is no garbage collection call. Because we compiled, not necessarily a single kernel, we can decide based off of fusion heuristics to make multiple kernels based off of the application or whatever else. But as a consequence, within the call to the Reactant function, there is no garbage collection because we've perfectly managed that ourselves on the inside.
Thank you. So this works for dense arrays, I guess. But what about sparse arrays, for example, sparse matrices or sparse vectors?
Yeah, so sparse arrays are partially supported in the sense that, if it can be built out of arrays, and regular sparse arrays are built out of arrays because that's a Julia primitive, we can convert it inside of here. That doesn't mean that you'll necessarily got the optimal sparse sort of matrix performance. That said, if we go look back at this sort of piece right here, right, where it's like, hey, you only extract out this one piece like you might do in a sparse array, actually our compiler optimizations, even if you didn't mark it as a sparse array but only happened to use part of it, will give you a lot of that same benefit as sparse arrays by default. The caveat here is this needs to be a structural sparsity as opposed to a data-dependent sparsity. So it just happens to be that a lot of these things are zeros. We won't currently optimize with that taken into account. If it's because you only read certain elements, we will take that into account. Adding native sort of sparse arrays, importing is something we're working on though.
Is there, I guess, if so, then more a long-term path to get part of this into the Julia compiler?
Yes, so there's a lot of things sort of ongoing at the moment, which range from sort of like Julia compiler plugins, custom abstract interpretation and the likes. We see this as sufficiently useful that, starting to work and play on this, especially all the optimization stuff that is going to be independent of whether or not it's a package or the native Julia compiler right now. I know the core Julia devs have been looking a lot at how to enable sort of custom compiler passes. Effectively, all this is a custom compiler pass inside of a custom abstract interpreter. Currently, Julia base doesn't support you being able to do special things with that on the inside, but as that sort of eases up, we can migrate more and more of this into base. What, sorry?
The third simplification might have a problem there.
In what sense? Did I write a bug on the slide or just?
Yeah, it's the missing transposes.
Oh, yeah. Fair enough.
One quick question. So you mentioned use CUDA JL to extract the LLVM.
Yeah.
And then you could optimize that with Reactant framework. So can I pass, like, let's say I have my own custom library and I extract LLVM out of it, use it, and can I just pass it to your framework and you could optimize the CUDA JL LLVM?
So the answer is yes. Ironically, we currently do something kind of similar for that from C++ because we don't have all this nice infrastructure like in Julia we can inject these pieces into. The caveat, right, is like we did a nice job setting this up to automatically hook in with CUDA.jl as the LLVM emitter and then, Razor inside of Reactant. So you might need to do a little bit more setup on your side to take your LLVM and hook it in, but all of the sort of transformation passes that we have here are general. You can start with LLVM and do whatever you like.
I feel like I'm missing something basic. It seems to me that you'd have a lot more information if you went from Julia to the raising step without compiling through LLVM. So clearly, I just missed. Why would you lose all that information in the nice high-level language?
So the answer is we don't. If you come from existing, like mapmuls or whatever else from, the base Julia operations, we will directly preserve that as saying like, hey, you wrote a matrix multiply inside of Julia. This becomes a matrix multiply directly from, in this case, the unoptimized code that we see. The caveat, right, is not all Julia code is based on top of, high-level linear algebra optimizations or, array operations, even though you can turn it into a bunch of individual slices. A lot of times people do write custom CUDA kernels, and we equally need to be able to support those custom CUDA kernels. So the majority of time that you use Reactant, assuming you're not calling into CUDA kernels themselves, it does directly preserve that high-level Julia semantics, but also it enables us to equally take low-level pieces that you've hand-scheduled or optimized or for any number of reasons chosen to write yourself, and we can still import and use that. Also, I apologize. I think we need to get to Avek's talk since we're now 5 minutes into his talk. Happy to take more of these questions offline.